All right, good morning, everybody. I'm happy to be with you again. It's been a while in this geotechnical earthquake engineering course since I recorded a new lesson. Much of my material has already been recorded in the past. Where I am recording right now, it is currently the first week of April in 2020. We are weeks into the COVID-19 pandemic, and I, along with all of my students, have been on quarantine for several weeks now. And so, to my students, this lesson is for you. It is another one of it deals with another one of the consequences and effects of an earthquake, which we have yet to discuss, but I want to introduce to you today, and that is the idea of seismic slope displacements. Now, the term that's more familiar to the public, I think, is seismic-induced or earthquake-induced landslides. But there are many forms of landslides, including rock falls, rock slips, rock topples, rotational deformations, infinite slope failure. The list goes on and on. So when I use the term slope displacements, it's a little more generic, and I think encapsulates a lot of the deformations that we're talking about. But understand that most of what I'm talking about in this lesson here relates to soil slopes and not necessarily rock slopes, though it could be applied to rock slopes if the parameters were calibrated and appropriate. So let's just jump in. By way of background, we've observed for many centuries that earthquakes have produced deformations of slopes, and these deformations have ranged from very small deformations with some visible cracks along the heads or the tops of the slopes, all the way to very large deformations where slopes have traveled over an extent of kilometers and buried villages or cities, and have been very devastating, and many individuals have lost their lives from this type of tragedy. So there's a table in the Kramer Geotechnical Earthquake Engineering textbook that summarizes or defines the different names for the different types of slope deformations we're talking about. It's table 10-1. And you can go and check that out and see for yourself and see some of the differences in these different deformations. So to boil it down, one of the most common tasks that a geotechnical earthquake engineer needs to do is the evaluation of slopes or embankments for stability during an earthquake or after an earthquake event. So currently, in current practice, engineers in practice today employ usually one or of two methods, sometimes both methods, to perform these types of evaluations. The most common method that has traditionally been performed is a limit equilibrium analysis or limit equilibrium methods. And the second that is rapidly gaining popularity and application in industry today are stress deformation methods. We'll talk about each of these, more about the limit equilibrium methods, but we will address a little bit the stress deformation methods. Now, before we go any further, I need to give you a disclaimer. I'm not going to delve into the details or the background of limit equilibrium analysis or stress deformation analysis. That's not the scope of this lesson. For that type of material, I'm going to refer you to a different course at BYU, one that I do not teach. It is the 544 class. It's entitled Shear Strength and Slope Stability. It doesn't mean that I cannot teach it. It just it has not been assigned to me, or I've not had the opportunity yet to teach it. And so for those of you at BYU who are considering another good either senior technical elective or graduate level class, if you enjoyed what you learned in this 545 class, then you will probably enjoy the 544 class as well in this shear strength and slope stability course. Instead, this lesson is going to focus more on the procedure itself and how to perform the analysis to get a number for the assessment. So let's just begin with the most basic approach. This is a method that is rarely applied in practice today in actuality, but it's a great introductory start. And it deals with the idea of resistance versus demand. And it's called the Simplified Coleman method. And all that we're doing with this method is we're taking a cross-section of a slope, and the slope has certain shear strength parameters, cohesion and shear strength, or cohesion and friction defined by the friction angle. And we're going to assume a linear failure surface from point A to B and defined by this angle beta. So that means that this overlying block wants to slide down slope. And so it has some driving force, which is the weight of it. And the resistance is going to occur along the shear plane, and that's denoted by these little arrows here. That's shear resistance along that plane. And so when we talk about demand is basically the weight of the soil slope, and the resistance is going to be the shear resistance along that shear plane. So typically when we talk about a slope stability analysis, we are defining that risk in terms of a factor of safety. And so in this case, the factor of safety is going to be the resisting forces along the shear plane divided by the driving forces from the weight of that section of the embankment. So the resisting forces can be quantified using this equation right here, where you see we have a component that is the cohesion. This L is the length of this line right here. So think of it as that distance right there, that's length AB, okay? And then we also have this frictional component on the right. And all that resistance force is going to be divided by the driving force. Now notice, by the way, that we haven't even introduced the possibility of an earthquake. This is just the factor of safety against a failure of the slope in this mechanism in static conditions under normal gravity. Now, if we want to account for the potential of an earthquake coming in as well, because we can't analyze this dynamically, or at least we don't want to, we're going to perform what's called a pseudo-static analysis. And in a pseudo-static analysis, what we're going to do is we're going to take the acceleration of the earthquake, and we're going to equate that to a force acting on our soil mass. So good old Newtonian physics, right, where force is going to equal mass times acceleration. We're going to equate that to this relationship right here, where we have K, this KH, which is essentially an acceleration. And then we have the weight of our soil, which is basically equivalent to the mass of the soil. So we have that in both the horizontal and the vertical directions, because we also have a vertical acceleration as well. Now, if we had a downward acceleration, that's just going to push the particles together and increase our resistance. So we're going to ignore that case, and we're going to look at an upward acceleration, where it's going to pull the particles apart and reduce the friction between them. So the upward acceleration is our critical case. Similarly, if I consider accelerations into my slope, that's just pushing the particles closer together and increasing that shear strength on the plane. So we don't want to consider acceleration in that direction. We want to consider acceleration down slope, where it's going to pull the particles apart and try to move that soil mass down slope. So if we want to consider then these components in there as well, then our equation gets modified. And now you can see that it looks a little more complicated. And it looks a little more complicated for a couple reasons. One, we have now these acceleration coefficients in the vertical direction and in the horizontal direction. But we also have what's called a reduced friction angle. And we also have a reduced cohesion that you can see. And the reason that they're reduced is from fatigue, from cyclic loading on the soil, the strain in the loading, it softens the soil, and it's going to reduce their shear strength or their shear resistance. And so we'll talk more about that later in this lesson, but typically that's on the order of a 20% reduction from static strengths. So the way that we're going to interpret this equation here, if the factor of safety equals 1, if we run this equation and this computed factor of safety comes right out to equal 1, then that means that this KH is equal to what we call KY, or the yield coefficient, or the yield, sometimes called the yield acceleration. It's the horizontal acceleration that just gets that soil mass sliding downhill. So that's why we call it the yield coefficient. And that has a special connotation, which we're going to use later in this class. But I just wanted to introduce that concept to you. Now, in the real world, nobody really uses the Coleman analysis. That's too simplistic. And the reality is that when slopes fail, they don't fail on a linear surface. They usually fail more on a curved or a log spiral shaped surface that looks like this. Now, there's no simple direct solution like the Coleman analysis that we can just solve with a simple equation. Because when this mass gets moving, we have not only shear along the shear plane itself, but we also have shear going on all inside of this soil mass. So there's just shear happening everywhere inside of it that we want to account for. And so this is where engineers many decades ago developed these what are called method of slices. And again, I'm not going to talk too much about the method of slices. It's discussed at length in our 544 class in our department. But what the only thing I'm going to talk about is when we solve these method of slices, we're analyzing each slice sequentially, one by one. And we start with one and we just move down the chain until we've reached and solved all of them. And each slice is analyzed much in the same way as the Coleman analysis, where now we have a linear surface on the bottom where we have a resistance, we have a weight of our slice. The only difference is now that we have potential for shear along the sides of our slices that we typically want to account for. And then it becomes a game of managing our number of knowns versus our number of unknowns. So there's lots of different methods for solving these that handle that problem, different assumptions that we make. The summation of moments equal to 0, the summation of forces equal to 0. A lot of these methods then are, for instance, the Morgenstern method, the Morgenstern and Price method, Bishop's method of slices, modified Bishop's method of slices, on and on and on. There's lots of different methods. We're not going to deal with those in this class, but I just want you to be aware of them, okay? When we do a pseudo-static analysis, we're just going to, it's the same thing as a static, we're just going to add an acceleration component to, each of the slices that we analyze. So when we perform a pseudo-static analysis, I mentioned that we reduced our shear strength components, the cohesion and the friction angle. And the question is, why do we think, or why do you think we typically need to reduce this? Well, it's because whenever I have cyclic loading, actually let's plot it like this. So in this axis, I've got shear stress. In this axis, I've got shear strain. And let's say I plot the testing of a soil such that it looks like this. And every time I cycle this in a test, I'm going to start to see deformations start to accrue in my loading of the soil. And eventually the soil is going to become very plastic, such that I'm going to start to see the formation of these kind of banana loop things, and I'm going to start to see some very large permanent strains develop in the soil. Each one of these, of course, is indicative then of the what we might call the backbone curve, which we talked about in a previous lesson, right? So if I were to take the tops of all of these curves, it might look something like this. So we've discussed that the more we strain a soil, we end up having a softening effect on the soil. And when we have cyclic induced slope deformations, boy, that's really softening the soil as well. And so for that reason, we due to that cyclic softening effect and also the potential for pore pressures to reduce the effective stresses in the soil, we are going to reduce those shear strengths. So typically, and what's done in practice is we reduce it by 20%. So we end up with 80% of the static or peak, the static cohesion and static friction angle. And all of this comes from a paper by, I believe, Tokimatsu and CEEN back in the 1980s. And everyone just kind of accepted it at face value, and they've been running with it for almost 40 years now. And we're starting to see that, just applying a generic 20% reduction may not be the best approach. Because 20% may overpredict the amount that we need to reduce it, or may underpredict the amount that we need to reduce it. And so we're starting to see research and methods give us more accurate ways to predict the amount that we need to soften it. But for the time being, in industry, most people today are still applying this 20% reduction. Another thing that we need to consider when we talk about shear strengths and softening is the idea of a progressive failure. Progressive failures are indicative essentially of strain softening behavior. This plot here is kind of a famous plot, or this schematic that shows different points along the bottom of a shear surface. And if we were to plot these points at different places on the stress strain curve, it might look like this. And so this point at A is going to experience the most strain initially. And so it moves along this stress strain curve quicker, and it's going to hit its peak strength quicker. But eventually, it's going to pass that strain and drop down and soften before all the other points do. And so if we make the fatal mistake of assuming that the peak strengths along these points, at points A, B, and C, all occur simultaneously in our analysis, we could be really shooting ourselves in the foot. Because what really is happening is, while, for instance, points B might experience their peak strengths, point A has already experienced its peak strength and has already softened. And so by the time points C reach their peak strengths, it's possible that points B and A have already reached their peaks and have already softened. So this type of unraveling or zipper type failure that begins from the center of the slope and progresses in both directions is what we call a progressive failure. I like to think of it as taking a zipper and ripping it open in the middle and just tearing it. because that's essentially what we're doing. So, in similar to this fashion, when we look at these types of strain softening plots, quite often this residual strength here is quite often much less than 20% of the peak strength. And if that's the case, then that 20% reduction that's usually applied generically in practice today may not be sufficient. And so if you have sensitive soils, you need to be very careful with this and make sure that you're applying the correct strength reduction, the correct softening, whenever you do your slope stability assessment. So here's a couple more things about performing a pseudo-static analysis and limit equilibrium methods. Typically, when I've done these analyses in practice, we neglected the vertical acceleration. And there were various reasons for doing this. We often observed its incorporation to be pretty negligible, though it shouldn't always be. And so horizontal has generally been considered to be the most important, but we do often neglect the vertical acceleration. But that's really up to the user, what they choose to do. The second point that is estimating that horizontal acceleration coefficient, KH, is typically viewed as the most difficult aspect of performing a pseudostatic analysis. There's a lot of rules of thumb out there, and folks go into practice and they get mentored by the senior engineers who are at their firms, and senior engineers usually just hand them a value and say something like, hey, just take 50% of the peak ground acceleration and you're good. And young engineers run with that, and they don't really know where that 50% comes from, but they don't really care because their boss told them to do it, and so they're going to do it. Other places, they'll apply some other multiplier other than 50% of the PGA. We're going to get into this a little bit more here in just a second, but I just want you to understand that this KH is quite often the most difficult aspect. And so that leads to my third point. When you are being faced with the selection of which horizontal coefficient you need to use, KH, the question you really need to ask yourself is, what kind of deformation can I tolerate? That's the question you need to be asking yourself, because the amount of deformation that your slope can tolerate is going to really control the acceleration coefficient that you put in there. And the ironic thing is, this point is almost always overlooked. Let's go straight to the source where we get this 50% coefficient. And by the way, that 50% multiplier for our KH coefficient that everybody seems to use, it comes from an example that was given in a research report from Heinz, Griffin, and Franklin. Now, Heinz Griffin is a brilliant engineer that works for the, at least for a time, I'm not sure where she is at this moment, but she was at the U.S. Bureau of Reclamation. And she did a lot of work with seismic deformations of dams, of earthen dams. And so you can understand why that community is very interested in deformations from earthquakes. And so in their paper, they presented these two figures right here. Now, in this one figure on the left, what we have is predicted deformation of the peak of the slope. That's going to be U in terms of centimeters, okay? And it on the x-axis, they have what they call the acceleration ratio. I'm not sure why they say it's N-A or N-A. Really what this is the yield acceleration divided by the maximum horizontal acceleration that we anticipate at the site. And quite often we assume some people will assume K max equals PGA, but we can't really make that assumption because that's going, we get K max from this plot here on the right. What we have on this plot on the right is this ratio of what's called Y over H, where Y is the height of our assumed failure surface within our slope or our embankment, and H is the height of the total slope or total embankment or total dam, whatever it is that we're dealing with, okay? So Y, if we have a full depth failure happening in our slope, if that's the case, then Y divided by H is going to equal 1. That would be like a full depth failure. If we have just a teeny little failure right at the slope, that's going to be something closer up here to Y over H, closer to 0. Down on the x-axis, we have what they call the amplification factor. And what this is this is the ratio of K max divided by the PGA, where PGA is normalized to G. So it's some percent or decimal of G, gravity. And so this is the ratio that they recommend. So then we have these different curves based on data that they performed or gathered from their study. They have the mean recommended curve. They have the mean plus 1 standard deviation. And then they have what they call the upper bound, which we interpret to be mean plus maybe 3 standard deviations. Okay, and down here on this plot, we see the same curves. We have the mean plus 1 standard deviation, and we have the mean plus 3 standard deviations, meaning the upper bound. Okay, now, this is text taken straight out of their research paper. And I'm just going to read it so you can just follow along. It says, the method, meaning their method for slope deformation prediction, is as follows. First, select an acceptable amount of permanent slope displacement. This is U in terms of centimeters, okay? Next, using the results of the sliding block analysis in figure 7, determine an acceptable acceleration ratio, which is the ratio of the yield coefficient to the peak average acceleration coefficient of the sliding mass. Okay, what that means is you're going to use this figure right here and use whichever one of these curves you deem sufficient for your project. You're going to start with whatever your acceptable deformation is, and you're going to come over to the curve and come down and get your corresponding ratio of ky over k max. That's all they're saying, okay? Then, using the depth of the failure mass relative to the dam height, together with the peak ground acceleration coefficient at the base of the dam, that's, remember, this is the ratio k max divided by PGA, determine the value of K max from the amplification factor in figure 11. That's, by the way, this figure right here. This is their figure 11. So we're going to use that figure to get our K max value. The amplification factor is the ratio of the average peak acceleration of the sliding mass to the peak ground acceleration at the base of the dam. Here we go. The pseudo-static seismic coefficient, KH, that you should use in your slope stability analysis is equal to ky. By setting kh equal to ky, if the resulting factor of safety is 1 or greater, then the expected slope displacement should be the acceptable amount of displacement or less. Alternatively, one could use the method in reverse. Start with the PGA for your site. One could determine the pseudo-static coefficient KH that corresponds to varying levels of displacement. So in other words, what she's saying is if you run a pseudo-static coefficient and you plug in your KY into your analysis, if your factor of safety is equal to 1 or greater, then you can rest assured that your displacements will be no larger than whatever your initial acceptable displacements were. If your factor of safety is less than 1, then you could potentially have problems. Alternatively, she's saying you can come in from this angle and obtain whatever your Kmax over PGA value is, and then given that, come in through whatever your Ky over Kmax value is, come up and predict whatever your displacement is. So you can go either direction in design, just whatever you choose to do. Okay, here's the example problem that shook the world, right? In their report, they give this example where they say, okay, let's use an example. Let's determine the value of Kh that we would use for a slope stability analysis if the acceptable amount of slope displacement is 1 meter. Assume a full depth failure surface. So that means y over h1 equals 1.0. Okay, so this is where things start to get really fun. Our assumed displacement is, or our acceptable displacement is 100 centimeters. That's 1 meter. And let's assume that we're using the upper bound curve, meaning the mean plus 3 standard deviations. So we're being uber conservative. So we're going to come over from our acceptable displacement all the way to that curve, and then we're going to come down, and we're going to get our value of Ky over Kmax. And that's going to equal about a value of 0.17, okay? Now, from this curve over here, we're also going to get our upper bound for a value of y over h of 1. We're going to come over to the same curve of the upper bound method, and we get a Kmax over PGA of 3.38. So I got those values for our example problem. So from figure 7, we get 0.17 for our acceleration ratio, and from figure 11 we get an amplification ratio of 3.38. Therefore, our Kh that we should use in our pseudostatic analysis should be equal to 0.17 times 0.338 times PGA. Okay, so because remember, we have Ky over Kmax times Kmax over PGA, and this right here is going to be equal to our Kh. So we multiply those values, and it comes out to equal 0.57 PGA. Awesome. So people, okay, a lot of people, they read this example, but they read it really loosely, and they just said, oh, she's just recommending that we use about 0.5 PGA, and they ran with it. But look at the assumptions that we're making in this problem. First, we're assuming if you use 0.5 as your Kh value, 0.5 of times PGA, we're assuming then that, I should clarify, I erased that. It's not just the ratio of Ky over Kmax times Kmax over PGA. It's those ratios times PGA. That's what's going to equal Kh. Okay, that's important that we note that. So people are just running with that 0.5 times PGA, but look, we assumed that a displacement of 1 meter was acceptable. And we also assumed that we wanted to use the mean plus 3 sigma standard, or 3 standard deviation curve, the 99.9th percentile curve, which is really, really conservative. And so what this ends up often doing is giving us some very large predicted displacements. And it's also, by the way, assuming that we can live or tolerate with 1 meter of deformation, which if we're dealing with for instance, a 300-meter tall dam, 1 meter of displacement may not be significant. But if you're dealing with I don't know, a 10-meter tall highway embankment, 1 meter of deformation could be serious trouble for your embankment. So you need to consider what you're doing when you do these types of problems. Now, let's just review then the procedure for evaluating seismic slope stability, okay? I've worked on numerous projects where I've done various procedures, but almost all of the procedures follow some sort of I guess, version of what I'm about to show you. And so what I'm sharing here is going to be very similar to any project that you'd work on in engineering practice today. So here it is. The first step is you need to check both the drained and the undrained static slope stability. Static meaning no earthquake, just looking at the weight of the soil itself. Then step number 2 is we're going to go to what's called post-seismic stability. I'll talk more about this in just a minute, but in a nutshell, post-seismic stability is like a post-liquefaction analysis. We're going to apply the fully softened or fully liquefied strengths to the soil and see if it can stand up under its own weight. If it can't, then we're going to assume that that leads to a liquefaction flow failure. Okay. If it can stand up after the earthquake, then the last step we're going to do is we're going to check its stability during the earthquake. We're going to look at the pseudo-static stability and look at the potential deformations from the earthquake if we deem it necessary. So with static stability, again, I'm not going to dive too much into this, but we're going to use these cases to evaluate the construction case, or the short-term stability, and the long-term stability of the slope. So no seismic loads are in this static stability. So for the construction case, we're usually going to use undrained shear strengths for the soil, and we're typically targeting factors of safety, acceptable factors of safety larger than 1.1 to 1.3, depending on the importance of the project. If it's a very critical project, it may require a factor of safety as high as 1.3 for construction. That's pretty rare, though. I usually saw projects around 1.1. For the long-term stability of the project, we're dealing with factors of safety targeting between 1.3 to 1.5 generally. Okay. All right, for our post-seismic stability, this is, again, we're applying shear strengths from after the earthquake. So this case is going to evaluate the static stability after liquefaction and cyclic mobility have weakened the soil, and all of the ground motions have ceased. So it's intended to evaluate the potential for a liquefaction flow failure, as we discussed before. So in this case, all of our soil layers that have been predicted to liquefy using the liquefaction triggering methods that we discussed in previous lessons, they're going to be assigned their liquefied steady state strengths. So we're going to reduce their shear strength substantially. Soil layers that are saturated or fine-grained that were not predicted to liquefy, we're going to reduce their shear strengths, typically on the order of 10 to 20%, like we discussed earlier, to account for pore pressure degradation and cyclic softening. So typically for the post-seismic static evaluation, we're looking at factors of safety, target factors of safety greater than 1.1 to 1.2. Anything less than that, we're going to assume a liquefaction flow failure has occurred. Now, here's the problem, right? Where do we get those static or those steady state strengths for the liquefied soil? We could try to sample the soil and measure them in a cyclic shear device in the lab, but that's really difficult to do because it's difficult to get an undisturbed sample into the lab, and it's difficult to find a lab that even has the right equipment to do this type of testing. So if we can't measure it in the lab, then we need to approximate it or estimate it. One of the most valuable tools that researchers have given us over the years are back-calculated steady-state strengths that they've documented and back-calculated from various flow failure case histories. And then they've correlated them back to various measurements of in-situ soil resistance. So these back-calculated shear strengths are called they're called residual shear strengths to distinguish them from steady state shear strengths that we actually measure in the lab. So we'll often use this term S sub U for the residual shear strengths. So just bear in mind that residual shear strengths, they're not actually measured. They're back calculated from usually a limit equilibrium analysis, sometimes now today using stress deformation methods and finite element. They're back calculated. So in other words, if we look at a case history where a large deformation occurred, the investigator asked a very basic question: what would the soil's shear strengths have needed to be in order to produce the deformations that I observed? And so then they back calculate those strengths using that question. For residual strengths today, engineers will rely on two popular methods. There's what are called uniform strength correlations, and there's normalized strength correlations. So uniform strength correlations are called uniform because they are independent of the soil's confining stress. Let me show you what I mean. Here is a plot of uniform residual shear strengths. This was developed by Seed and Harder, not Harry Seed, but his son Ray Seed, and one of his early PhD students named Les Harder. Both are good guys. And they published this method in 1990, and these are all back-calculated shear strengths from limit equilibrium analyses. Now, they did not normalize or account for the confining stress of these different soil layers. All they did was they came up with the undrained shear strength. This is the equivalent of the cohesion of the soil, assuming zero friction of that soil layer. My wife just came in and asked me a question. I'll be done in maybe 15 minutes. And she looked disappointed. So she needs this room. Sorry, guys. I'm confined in my house, so I have limited space. So they're uniform shear strengths because they are independent of the confining stress. Okay. So it doesn't matter if the soil layer is at a depth of 100 meters or if it's a depth of 1 meter. We're still going to use the same residual strength for the same plot. Now, for normalized residual shear strength correlation, these assume that S sub U depends on the effective vertical stress or the confining stress. So these are presented in terms of a ratio of undrained residual strength divided by the soil's confining stress. Now, these were popularized originally by Stark and Olson, where they published a paper in the early 2000s. And then other researchers have come along and they've also published a lot of normalized shear strength methods for liquefaction shear strengths. Most recently, the author of our textbook, Steve Kramer, and one of his PhD students named Wang they developed a normalized residual shear strength method that was very well received. In fact, it was awarded, I believe, the Norman Medal from ASCE, their paper, in like 2018 or something like that. And so, but it was interesting because they developed the method more than 10 years prior to that. So I'm presenting to you a method that is actually an averaged method. It comes from Ledesma and Bray, from Christian Ledesma's PhD work. He was a PhD student of Jonathan Bray at Berkeley, and they developed, what they did was they took all these different methods for normalized residual shear strengths and they plotted them up. And they just said, okay, all these different methods represent the epistemic uncertainty, our uncertainty in predicting residual shear strength. So they developed then a curve to all the different methods. And this equation right here represents the mean of that curve, the best fit. And then the scatter of all the models represents the uncertainty. And so that standard deviation of that scatter is given by this value right here. So I like this method. You can see that it's just a function of the clean sand, energy and confining stress corrected SPT resistance, standard penetration test resistance, or the blow count of the soil. So we can easily approximate the shear strength of the soil if we can come up with the confining stress, or an estimate of the effective stress of the soil at its depth, and we can measure its SPT resistance. So a couple of things. If some of you may be going, well, which do I use? Do I use the uniform shear strengths like from CEEN and Harder, or do I use the normalized residual shear strengths from guys like Ledesma and Bray, or Kramer and Wang, or Stark and Olson? Here's some findings from my own research that I'd like to share with you. And I've done a lot of research on actual case histories from the field and test data. And so we've observed a couple things, and a lot of these things we've published in the literature. And I'll share these with you. So first, we've observed that the uniform residual strengths, using the CEEN and Harder method in that plot, they're usually greater than the normalized residual shear strengths up to depths of about 10 meters, or about 30 feet below the ground surface. Around depths of about 30 meters, both methods give you about the same shear strengths. At depths greater than about 10 meters or 30 feet, then the normalized residual shear strength methods give you larger shear strengths. We observed that at shallow depths, so at depths less than usually about 5 meters, I would say, the normalized methods, the SU over sigma methods, they can give you unrealistically low shear strengths at these shallow depths. And that's because they have very low confining stresses. Okay. So instead, we found that at shallow depths, the uniform residual strengths were much better and gave us better fit to the actual data from the field. However, it reverses. When we got to deeper depths, the uniform residual strengths gave us lower strengths than what we observe in the actual case histories from the field. Another thing to consider, and this is hard, right? If we look at both of those methods, they're really fine-tuned towards soils that have blow counts less than about 16. Beyond a soil, or for soils that have blow counts greater than 16, there's really no data to support what we should do. So engineers are all over the map with what they do. Some engineers extrapolate lines at blow counts greater than 16. Some just wave their hand and say, we won't have a problem. There is no liquefaction at blow counts greater than 16, which we know that's not true. Now, there may be no deformations at blow counts larger than 16, but there's certainly liquefaction at blow counts larger than 16. The problem is that there's little to no real-world evidence of flow liquefaction failure in soils with blow counts greater than 16. In fact, there is no real-world evidence to date of such an occurrence. So we're still guessing. I mean, is it because it really doesn't happen, or is it just because it hasn't happened yet? And the problem is we don't know. So for pseudo-static stability, this case is going to evaluate the dynamic stability of the slope when exposed to the prescribed horizontal accelerations. Usually we're using values of 0.5 PGA because that's usually prescribed. So if 0.5 PGA is equal to your KH value and your factor of safety is greater than 1, that means that you can rest assured that your horizontal slope deformations are going to be limited to 1 meter or 0.1 to 1 meter. If you can't live with a 1 meter deformation, then you need to adjust your KH factor. If your factor of safety is less than 1, then you're likely going to see larger slope deformations, and a deformation analysis will probably be required. We'll talk about this in our next lesson. But this is usually going to require that you compute the yield acceleration of the slope. In other words, what a KH value gives you a factor of safety of 1.1. So finally, the question of all questions, and this is a question I am asked a lot by engineering practitioners, and it is, do I couple reduced soil shear strengths with the addition of a pseudo-static coefficient? And the argument here is, in order to reduce the shear strength and the stiffness of the soil, it requires ground motions. So both soil softening and ground motions really don't happen at the same time. The ground motions need to happen first so that the soil can strain, and then through strain the soil softens. The question is, can that softening and accelerations occur simultaneously? We call this a coupled or an uncoupled analysis. So the coupled analysis is going to assume that liquefaction triggers early in the ground motion, and that significant ground motions remain after triggering. So we have residual strengths in the soil at the exact same time that we have ground motions. So we couple residual strengths with pseudo-static acceleration coefficients, and that's going to result in some pretty large deformations of our slope. The alternative theory is an uncoupled analysis. So this is going to assume that liquefaction occurs later in the time history, and that by the time the soil softens and residual strengths are developed in the soil, most of the significant or all of the significant ground motion have already occurred. So in this instance, when we apply those residual shear strengths in the soil, we are not going to apply a pseudo-static acceleration. So the question that everyone asks, should I do a coupled analysis or I should do an uncoupled analysis? Here's my opinion. And this is after many discussions with many smart experts on this topic, and based on my own conclusions from what I've seen from the field and from testing. Unless you have an analysis that suggests that liquefaction will not occur until later in your design earthquake, or unless your client specifically prescribes an uncoupled approach and hence assumes the liability themselves, I would definitely recommend that you use a coupled approach. Okay, folks, that's the end of this lesson. Thanks for your attention, and I'll look forward to talking about how we can compute deformations from pseudo-static analyses in the next lesson using Newmark sliding block methods. Have a great day.